When we hold our breath, the air in contact with the alveolar becomes poor in oxygen. The body reacts by contracting the diaphragm in order to shake up and remix the air in the lungs. Therefore, air that is a little richer in oxygen comes into contact with the wall of the alveolar. When this has also become impoverished, the diaphragm contracts again. After a few times, this shaking up is no longer effective, and as a consequence, a hypoxic syncope occurs. The density of oxygen molecules in an alveolar also depends on its volume. On ascent, when the pressure decreases, the volume of the alveolar increases and molecules of oxygen become sparser. Holding your breath underwater for too long means risking a hypoxic syndrome, shallow water blackout, during the last few meters of the ascent when the pressure decreases rapidly. Air starvation. Let's now examine a situation that occurs more often than you think. Breathlessness, a succession of fast, short, involuntary breaths. When we breathe, we use only a minimum part of the total capacity of our lung volume, about half a litre of a variable total of between 5 and 8 litres. Before arriving in the active area of the alveoli, the air passes through a series of rigid cavities, nose and mouth, pharynx, larynx, trachea, bronchus, etc. Gas exchange does not take place in these cavities, and they are therefore known as dead air spaces. These have a volume of about 0.15 to 0.2 litres. So, with each breath we take, the first air that arrives in the lungs is the air we exhaled the last time we breathed out, and which stayed in these dead spaces. When we breathe through the snorkel, the dead air spaces increase by around 0.2 litres, further reducing respiratory efficiency. To overcome this, we must breathe more deeply than normal. Although our body burns oxygen, the main stimulus to breathe is activated by the amount of carbon dioxide present in the blood. If respiration is shallow, it is not very efficient, and not enough carbon dioxide is eliminated to interrupt the stimulus to breathe. In this way, a vicious circle is created that makes you breathe faster and shallower, creating a sensation of breathlessness. This is air starvation. To overcome this situation, it is enough to stop the activity that is making you breathless and take some deep breaths while trying to expel as much air as possible from your lungs. This cleansing reduces the level of carbon dioxide and increases the oxygen level. The breathlessness passes immediately. Hyperventilation. These deep inhalations and prolonged expirations that help breathlessness pass are similar to those made by free-diving record breakers before they make their descents in the hyperventilation phase. Although the method is the same, the aim is different. Both methods try to lower the level of carbon dioxide, but in the case of air starvation, it is to bring the level back to normal, while in the case of hyperventilation, it is to lower the level as much as possible, well below what is considered normal, in order to delay the stimulus to breathe. Let's take a look at the partial pressures of these two gases. An increase in the partial pressure of carbon dioxide corresponds to a decrease in that of oxygen. Hyperventilation is not able to increase the amount of oxygen available, but helps to lower the initial level of carbon dioxide, therefore delaying the contractions of the diaphragm. Prolonged hyperventilation can therefore be dangerous. Lowering the initial level of carbon dioxide too much could mean that the level of oxygen becomes too low before the stimulus to breathe is felt. body's reaction to this low level of oxygen is a hypoxic syncope. This type of syncope also tends to generally occur in the final meters of the ascent, when the pressure decreases rapidly. The best way to prolong a free dive is to move very calmly in the water and relax mentally. Avoid prolonged hyperventilation. Just 2 or 3 deep breaths at the most are sufficient before diving under the water. The Taravana syndrome is another danger linked to hyperventilation. This may occur if you make a series of long, deep, breath-holding dives, separated by a short interval on the surface during which you hyperventilate. However, this can provoke a gas imbalance and can even lead to the formation of gas bubbles that can, partially or totally, block the blood flow to some of the tissues in the body. The buddy system. The way to make skin diving safer, easier, and more fun is to use the buddy system, meaning you and your buddy take it in turns to make a free dive. While one person is under the water, the other watches from the surface, ready to intervene if necessary. Obviously, each skin diver must limit the depth of the free dive to that which can be easily reached by the other buddy. But what should you do if you are in a large group? That's simple. Just divide into pairs. In the previous module, you learned that a pressure imbalance in decompression, that is, during the ascent, may lead to the tearing of a membrane. If you breathe air from an aqualung under the water and then ascend holding your breath, you will create a pressure imbalance in decompression in the lungs. In fact,